Welcome, nocturnal minds aboard. Your learning journey starts now. Alright, picking up from our discussion on the general landscape of scientific explanation and modeling, let's now focus on a specific, often controversial approach: the feminist perspective within the philosophy of science. This isn't just about adding women to the mix, it's about fundamentally questioning how we think about objectivity and knowledge itself. So, where does this idea come from? Lynn Hankinson Nelson and Jack Nelson pointed out back in 1996 that feminists weren't just talking about the same old stuff as traditional philosophers of science, things like objectivity, truth, evidence, all that jazz. They agreed on wanting to understand these concepts, sure. But, and this is key, they fundamentally disagreed on what explanatory principles should be used in philosophy of science. It's like agreeing on wanting to bake a cake, but arguing fiercely over whether you use flour or cornstarch as the main ingredient. Pinnock's chapter here breaks down this tension into 4 neat parts. First, why the traditional crowd often waves the feminist approach away. Second, why we should actually consider it a legitimate philosophy of science. Third, is it actually better than the traditional stuff? And finally, a rather interesting twist, suggesting maybe we should ditch the approach label and think about it more as a political stance instead. Let's unpack that dismissal first. Okay, so why do many traditional philosophers of science just shrug and say, "Feminists, what now?" Pinnock points out it's often because they see it as irrelevant to the really hardcore stuff: physics, chemistry, biology. You know, the fields they think are pure, abstract, totally detached from messy human contexts. They might grudgingly admit, okay, maybe it has some point for sociology or psychology, but for the physical sciences, nope. Think of it like this: calling something Republican philosophy or blonde philosophy sounds weird, right? Those labels tell you something about the person, maybe their background, but not necessarily about the quality or validity of the philosophy itself. Traditionalists argue similarly: the gender of the scientist doesn't matter when it comes to justifying scientific claims. So, if the feminist approach is just about gender bias, then it's dismissed as irrelevant noise. Kurji nails this: feminists worry about values influencing science, while traditionalists say science is about explanation and application driven by cognitive goals, not feelings or biases. It's a fundamental disagreement about what drives science. Now, this dismissal rests on a couple of big assumptions. First, it assumes there's a clear, agreed-upon list of core questions in philosophy of science. Think of it like having a fixed menu for a fancy dinner party. Second, it assumes that whatever feminists say, it's definitely not going to touch those core questions on the menu. Pinnock immediately pushes back: is there really such a fixed menu? Or is it more like Wittgenstein's rope, constantly shifting and changing as science evolves? Maybe the core questions aren't carved in stone but are more like the range of things scientists and philosophers actually grapple with. From deep metaphysical questions about reality's structure to the nitty-gritty details of designing experiments. And what do we want science to do? We want it to tell us about the universe, sure, but also to be a reliable tool for learning how to learn. It's this broader expectation that feminist critiques might tap into. So, if Kurge's description is right, feminists face a potential knockout punch. How can they respond? Well, here's a clever countermove. What if they could show that feminist insights specifically about gender aren't just some side issue, but are actually essential ingredients for any good theory of science? Imagine proving that sugar is necessary for baking bread. Suddenly, anyone who wants to bake bread better needs to reckon with sugar. If feminists can demonstrate that gender plays a necessary role in understanding how science works epistemologically and how it should be done methodologically, then traditional philosophy of science has no choice but to incorporate it. It would have to redefine itself. So, the big question becomes, is this feminist challenge serious enough to force such a radical rethinking? That's what Pinnock aims to explore next. Okay, before diving deeper, let's clarify what Pinnock means by the feminist approach as a philosophy of science. She narrows the focus specifically to the physical sciences. Why? Because as Harding and Hintika noted way back, if bias is going to be a problem, it's got to be tackled in the hard core, the supposedly most objective parts of science. Not just the social sciences, where bias is already obvious. Think about it. Saying social science is biased isn't exactly groundbreaking news. But claiming the same for physics or chemistry, that's a much bigger deal. So, Pinnick stresses this isn't about demanding fair play or equal opportunities, though those are important. It's not about challenging basic scientific methods. Instead, it's presented as a claim about what makes the best epistemology and methodology for science. If this holds water, then traditional philosophy of science, by its own standards, is missing something crucial. Now, how do we judge this feminist challenge? Pinnick sets a specific criterion. She's looking at well-formulated arguments. This is important because it means some influential feminist work, particularly that which deliberately avoids formal argumentation, gets set aside for this particular assessment. Thinkers like Donna Haraway, whose work is often more narrative and conceptual, fall outside this scope. Similarly, titles like Beyond Epistemology or statements that the feminist project simply replaces the old malastream epistemology are probably too broad or non-argumentative to fit this focused analysis. The goal is to assess the logical force of the arguments presented as a distinct philosophy of science. So, who are the heavy hitters in this arena? Pinnick identifies two central figures, Sandra Harding and Helen Longino. Their work, she argues, is the bedrock upon which the feminist approach to science stands. Everything else, she suggests, is kind of building on their foundations. It's worth noting the distinction between feminist epistemology in general and feminist philosophy of science specifically. Harding and Longino are primarily known for the latter. Their arguments are described as innovative, provocative, and posing a real challenge that demands a response. If they're right, philosophy of science needs a major overhaul, especially concerning gender. Let's start with Sandra Harding. Her approach is framed as being friendly to science. She's not trying to tear it down, she wants to improve it. Her central thesis is quite bold. Science can only achieve its stated goals, things like objectivity and reliable knowledge, if gender is considered an essential part of its epistemology. Think of it like saying, to build a truly sturdy bridge, you must account for wind direction. And that wind direction is inherently linked to the gender of the architect. Harding essentially claims gender isn't just a footnote, it's a fundamental condition for scientific rationality. How does Harding make this case? She draws on several key ideas from her work. First, she argues that women and men literally occupy different geographical locations in the world, leading to different experiences, interests, and ways of thinking about knowledge. Because of this, starting research from women's lives, she claims, can actually lead to a richer, more complete understanding of nature's regularities everywhere. It's like having two different maps of the same territory, revealing different features. Second, she contends that the traditional definition of objectivity, often tied to masculine norms, actually distorts science. Finally, she proposes standpoint approaches, particularly those rooted in women's experiences, as the key to achieving what she calls strong objectivity. This strong objectivity isn't just about avoiding bias, it's about actively seeking out perspectives that reveal hidden truths. Harding's argument hinges on two crucial empirical claims. First, she asserts that gender biases scientific reasoning. Now, she likely implies that male bias is problematic, while female bias is beneficial, or at least offers a different valuable perspective. But how does she prove this without assuming it's true from the start? It's a tricky circularity problem. Her main strategy is to point to historical examples, often from biology, where male-dominated science led to skewed results, suggesting that a different, perhaps female-informed, perspective would have been better. Second, she claims that simply including more women in science will objectively improve its aims, increasing knowledge. Interestingly, later in her career, Harding seemed to shift away from the term standpoint theory, preferring labels like multiculturalism. Pinnick argues this is just changing the name, not fundamentally revising the underlying idea of specific groups having unique epistemic contributions. So, how do we evaluate Harding's case? On one hand, using history to support an argument is a perfectly legitimate method, something even philosophers like Lawton valued. It shows she's taking the challenge seriously. But here's the rub: where's the hard evidence? As Klee points out, Harding and her colleagues haven't provided solid data showing that, when marginalized people do science, their results are objectively better than those of the male elite. We're left with anecdotes, like Keller's stories about cellular life, or untested what-ifs about famous studies. While the promise is attractive, the empirical foundation seems shaky. The history of science dominated by men, ironically, seems to suggest maximizing male bias might be the winning strategy, which undermines Harding's point. It's a serious challenge, but it lacks the empirical muscle needed to convince skeptics. Next up, Helen Longino. Pinnock focuses here on Longino's contributions specifically to philosophy of science and epistemology, not her broader work in history or sociology. Longino's arguments are interesting because they're less explicitly framed as feminist in the sense of women's standpoint and more about the social nature of science. She talks about epistemic communities, groups of inquirers who share norms and practices. Since women form such a community within science, Pinnock includes her under the feminist approach umbrella. Longino's goal is ambitious: to develop a new way of thinking about scientific knowledge that integrates the social aspects, arguing that social interaction is actually what secures scientific knowledge. This directly challenges traditional views that emphasize individual reason and logical deduction. Longino's core argument revolves around evidence. She says evidence isn't absolute, it's relative to our background beliefs. And guess what? Those background beliefs are often biased. So, the solution: bring in better background beliefs, perhaps those informed by diverse communities, including women's perspectives. Better beliefs lead to better science. Klee's interpretation is blunt: it's about putting politically progressive people in charge of defining facts and methods. In her later work, Longino promises a new account integrating the social and the cognitive, claiming that social interaction is the key mechanism securing knowledge. It's reminiscent of Bacon's vision of a scientific community adjudicating truth. Does Longino's communitarian approach hold water? First, the idea that social interaction contributes to science isn't new. Loudon and Hall argued similar points. The feminist claim needs to show it's uniquely better or necessary. But here's the problem: Longino never demonstrates that feminist background beliefs actually lead to better science. There's no evidence that scientists who identify as feminists produce different or superior results compared to non-feminist scientists. Why should a community, especially one defined by gender or politics, have a special claim to uncovering unbiased truth? How do we know they get closer to unadulterated evidence than, say, individual male researchers? Longino tries to sidestep relativism by appealing to normative sociology rules for good communities rather than epistemology, but the core challenge remains: does this social epistemology actually improve our grasp of reality? So, wrapping up Pinnock's assessment of the feminist approach as a philosophy of science, both Harding and Longino offer intriguing, provocative ideas. However, neither provides the necessary empirical backbone to prove that their specific approaches actually improve scientific understanding or provide a better philosophical account of science. They present compelling arguments, but they remain unsubstantiated promises. This isn't just an academic quibble. If the rationale for promoting women in science relies on this flawed epistemological argument, it risks wasting precious resources. But, and this is crucial, Pinnock cautions against throwing the baby out with the bathwater. The failure of this specific philosophical approach shouldn't make us dismiss the broader political goal of feminism in science. Why? Because the evidence for discrimination against women in science is stark and undeniable. Despite more women entering STEM fields, they remain significantly underrepresented, especially at the highest levels in academia, particularly at top universities. Interestingly, the private sector sometimes offers better career paths for women than academia does. The idea that sexism is just a thing of the past in universities is demonstrably false. So, for anyone concerned with equal opportunity, the political thesis of feminism remains incredibly relevant and urgent. Understanding why the specific epistemological arguments falter is still important, though, precisely because clinging to them can distract us from the very real practical barriers women face in scientific careers. We need both the political push and a clearer understanding of the epistemological claims. For those interested in digging deeper, Pinnock provides a helpful reading list. For the empirical side, Look at the National Research Council reports and Sonnert and Holton studies on gender in science careers. For the philosophical arguments themselves, Longino's science as social knowledge is essential, alongside Duran's overview, and Griffith's and Whitford's collection. And for critical perspectives, Kirch's edited volumes, including A House Built on Sand, offer significant challenges to feminist epistemology, alongside Pinnock's own critiques. It's a rich field with ongoing debates. Alright, shifting gears now from the specific challenges of feminist epistemology to a more general model of reasoning that pops up frequently in science, inference to the best explanation. This is Peter Lipton's take on it. So, what's the big deal with induction? Science constantly involves making judgments about evidence. Does this data support my theory? Does it contradict it sometimes, like if an experiment flatly disproves a hypothesis, the connection is deductive, rock solid? But most of the time, especially when we jump from specific observations to general laws, it's inductive. Think predicting the sun will rise tomorrow because it always has, or inferring gravity exists because apples fall. These aren't guaranteed truths. The data could be misleading, or the hypothesis could still be wrong despite the data. Philosophers have struggled for centuries, since Hume basically kicked off the modern debate, to figure out how induction actually works. It's a notoriously difficult problem. Enter inference to the best explanation, or IBE. This idea, traced back to Peirce and developed by thinkers like Harman and Thagard, offers a model for many inductive leaps. The core idea is simple. We infer the hypothesis that would, if true, do the best job of explaining the evidence we observe. Think about it. Darwin didn't see natural selection directly. He inferred it because it explained the patterns in biological diversity. An astronomer sees redshift and infers recession because that's the best explanation for the observation. A detective finds fingerprints and infers Moriarty did it because that hypothesis explains the clues best. Notice, it's not deductive proof like Holmes sometimes pretends. It's about finding the most plausible story that fits the facts. IBE connects nicely with the idea of self-evidencing explanations. This sounds paradoxical, but it means the phenomenon we explain helps confirm the explanation. The galaxy's recession explains the redshift. The redshift confirms the recession. It's a virtuous cycle. IBE takes this further, suggesting that explanation comes before inference. Normally, we might think we first decide which theories are true, then use them to explain things. But IBE flips it. We evaluate how well different hypotheses explain the evidence, and based on that evaluation, we decide which hypotheses are worth accepting. We infer the best explanation. Importantly, we distinguish between potential explanations, which could explain something if true, and actual explanations, which are true explanations. IBE says we infer that the hypothesis offering the best potential explanation is likely the actual one. Why bother with IBE? It aims to solve two problems describing how scientists actually reason, and justifying whether that reasoning is rational. Lipton focuses mainly on the descriptive aspect. Traditional models struggle. Simple enumerative induction, predicting more of the same, is too simplistic and falls apart with riddles like the Raven paradox. The classic hypothetical deductive model, test hypotheses by deducing predictions, allows almost anything to confirm anything, which is absurd. IBE tries to bridge this gap. It allows for vertical inference, jumping from observations to unobserved entities, like inferring atoms from Brownian motion, but it's not wildly permissive. It demands that the hypothesis not only explain the evidence, but explain it better than competing hypotheses. It picks a winner. Okay, IBE sounds good, but it needs fleshing out. What exactly makes one hypothesis explain another observation? Using standard models like Hempel's deductive nomological model, where explanation is deduction from laws, leads to problems and basically reduces IBE back to HD. So, we need a better account of explanation itself. Even harder, what makes one explanation better than another? IBE implies we pick the single best, but scientists often entertain multiple possibilities or reject all. So, maybe it's inference to the best of the available competing explanations when the best one is sufficiently good. But what counts as sufficiently good? And what are the criteria for best? This is where the real work begins. A crucial question arises when we say best explanation. Do we mean the most likely one, or the one that offers the greatest understanding, the loveliest one? Think about explaining why opium causes sleep. Saying it has dormitive power is very likely true, but it's not lovely. It tells you nothing about how it works. I.B.E. Lipton argues should be about inference to the loveliest explanation. Scientists don't just pick the most probable hypothesis. They look for the one that provides the deepest insight. The claim is that the loveliest explanations tend to be the most likely ones. Scientists use loveliness as a guide to likelihood. This raises three challenges. First, identify what makes an explanation lovely. Second, show that lovely explanations usually are the most likely. Third, show that scientists actually use loveliness to judge likelihood. First challenge, identification. What makes an explanation lovely? Candidates include scope, explaining lots of things, precision, accuracy, mechanism, revealing how something works, unification, tying together disparate facts, and simplicity, elegance. These sound good, but defining them precisely is tough. Is simplicity just fewer words? Unification just fewer equations? Some worry these are just artifacts of how we phrase things. A different angle comes from contrastive explanation. Often, we ask why rather than Q. The goodness of an explanation depends on this contrast. Explaining why Mercury rises, not falls, is different from explaining why it rises, not breaks the glass. A good explanation needs a cause that makes the difference between the actual outcome and the alternative. This helps pinpoint what counts as a good causal explanation. Second challenge, matching. Do lovely explanations tend to be the most likely ones? Here, the picture looks promising. Features we value in explanations, like scope, precision, mechanism, unification, simplicity, often seem to be features that also make a hypothesis more likely to be true given the evidence. A theory that explains more accurately is generally better supported. The overlap isn't perfect. Sure, the dormitive power example shows a likely but unlovely explanation, but I.B.E. can handle multiple explanations. Contrastive explanation also helps. Remember Semmelweis and childbed fever? He noticed a difference between wards, asked why ward E versus ward R. Ruled out hypotheses that didn't explain the contrast, and landed on the infection hypothesis. This pattern, seeking explanations that account for contrasts in the data, is central to controlled experiments and seems deeply tied to finding the best explanation. Third challenge, guiding. Okay, lovely explanations tend to be likely, and they explain contrasts. But does that mean scientists actually use loveliness as their guide to likelihood? Critics might say, yes, lovely explanations match likelihood, but that's because inference follows Mills methods or Bayesian probability rules. If precision lowers prior probability, then high precision automatically boosts posterior probability, regardless of understanding. The defender of I.B.E. is in a tricky spot. Showing the match highlights the overlap with other theories. But there are ways out. First, I.B.E. might just get the extension right, capturing more real-world inferences than competitors. Second, the match itself needs explaining. Why should the most understandable explanations also be the most likely? I.B.E. offers a Darwinian-style answer. If scientists naturally select hypotheses based on explanatory virtues, then the match with likelihood is no surprise. Unless opponents provide a better explanation for this correlation, I.B.E. stands strong. How does I.B.E. relate to Bayesianism, the view that belief is just probability updating via Bayes' theorem? Some see them as rivals, but Lipton suggests they could collaborate. Bayesians have a neat formula for confirmation: P of H given E equals P of E given H times P of H divided by P of E. But applying it requires knowing probabilities like P of E given H, the likelihood. How do we estimate that? Maybe we judge it by how well it explains E, that is, its loveliness. If loveliness correlates with likelihood, then I.B.E. could provide a practical way to assess the likelihood needed for Bayesian updates. Alternatively, explanatory virtues like simplicity or unification might directly influence our initial priors, P of H, and priors feed into the Bayesian calculation. So IBE's focus on explanation could be woven into the Bayesian framework. Beyond describing how we reason, IBE has been used for a big justification project, arguing for scientific realism. The argument goes like this: our best scientific theories are wildly successful at predicting things. What's the best explanation for this success? Their truth. Therefore, we have reason to believe our best theories are approximately true. Sounds plausible, right? But it faces serious objections. First, it might beg the question, if we accept theories using IBE, can we then use IBE again to justify IBE's truth? Second, is truth really the best explanation? Couldn't a competing theory that just happens to make the same predictions explain the success just as well? Or maybe success is just due to scientific progress weeding out bad theories, not necessarily truth. Third, the explanation offered by truth seems logical, while scientific inference is often causal. Finally, it might commit a fallacy of division. Just because most losing lottery tickets have wrong numbers doesn't mean tickets with some right numbers are winners. Success doesn't automatically imply truth. For those wanting to dive deeper into these issues, Lipton provides key references. Hume's inquiry is the classic starting point for induction. Hempel's work is foundational for scientific explanation. Harman's paper was a major early push for IBE. More recent discussions include works by Taggart-Day and Kincaid, Barnes, Sillos, and of course, Lipton's own book. It's a vibrant area of research with plenty to explore.